All right, so welcome back to part C of this lecture, 16. In the first part, and here I've actually moved back here a couple slides to part A. In the first part of this lecture, we showed that the problem of optimizing polynomials could be formulated in a convex manner, convex optimization. We then showed that by constraining our decision variables to be polynomials of some bounded degree d, we could represent this optimization problem in finite dimensions, right? So we could have a finite dimensional decision variable, finite d dimension. And once we made that substitution, right, the optimization becomes linear in those decision variables. And then the problematic question was how to enforce these kind of positivity constraints, where this constraint has to hold at all values of x. So x is an independent variable here. It's not a decision variable, independent variable, which parameterizes where this inequality holds, right? It has to hold an infinite number of points, all of these x. And then we showed in part B of the lecture that constraints of this form could be enforced by requiring that these polynomials be sums of squares. So equals some q of x, where q is constrained to be a sum of squares polynomial. So we can replace these constraints, right, we'll put a negative sign in front of that, with, I can't actually erase that, but I can erase that way, with the constraint that that be sum of squares. Right. And I've argued that this can be enforced using LMIs, right? So the constraint that a given polynomial be sum of squares can be enforced as equal to zd of x q zd of x, where q is greater than or equal to 0. And so all that remains then is, so this is now a decision variable q, right? And likewise we have one here, equals, here I'll just write it out explicitly here, equals zd of x q1, let's say, zd of x. And this we replace with equals zd of x q2 zd of x, where q1 and q2 are both positive semi-definite. Right. So now we have some new variables, decision variables, right? q1, q, and 2, with matrix positivity constraints, but we've replaced this for all x constraint as an inequality with an equality, right? So we have to have that this constraint is satisfied with equality for all x. Now, because these are polynomials, however, right, we just need a way of relating the coefficients on the left and the right-hand side, matching coefficients, which is going to give us a constraint between C1 and Q1, an equality constraint of the form, let's say, A, and then we have a vector version of Q, but we'll get into that in a second. So we need to be able to enforce these constraints, these polynomial equality constraints, and then we can solve this SOS optimization problem. So now let's go back to where we were in our slides here. So the basic problem is on the left. We have C transpose Z, let's call it 2D of x, equals, and let's just say, make it simple, equals ZD of x, Q ZD of x, right? So we're looking for constraints of this form. Right. And this, of course, enforces the constraint that this is sum of squares. Right. So how do we enforce these constraints? Well, if this was a linear representation, right, if this was equal to, say, m, transpose ZD of X? Well, we would just need to make C transpose equal to M transpose, and we'd be done. However, of course, it's not a linear representation. It's a quadratic representation on the right and a linear representation on the left. And so what we need to do now is show how to reformulate a quadratic representation in terms of a linear representation. How to reformulate a quadratic representation as a linear representation. Right. So again, right, we're looking for equality, and if we had a linear representation, it would just be matching the coefficients. Unfortunately, of course, we've got a quadratic representation, so it's not quite that simple. So to do this, and here I've actually written out the formulae for how one does this. Well, first of all, I'm going to write out, it's a little bit of bookkeeping here, right? I just write out each of these monomials parameterized by the exponents of the monomials. So if ZD is, say, 1x, xy, for example, then your alpha 1 here is 0, 0. Alpha 2 is 1, 0, because exponent of 1 on the x and 0 on the y. And then alpha 3 is 1, 1, because an exponent of 1 on the x and 1 on the y. Right? So that's just how we represent these monomials using sort of these integer representations. It's just a bookkeeping tool. Right. So now what we're doing is we've got this quadratic representation. We want to write it as a linear representation. Right? So obviously it's linear in our decision variables. Right? Again, decision variables. And so the first thing we have to do is find a way to write the decision variables as a vector, because right now it's a matrix. And so the simplest way to do that is just to write out the vector form of that matrix, right? So basically what that does is you take the columns of the matrix, M1, M2, M3, so on and so forth. So the vector form of that is just the columns concatenated, M1, M2, and M3. So you make a rather long vector there, consisting of all of the columns of M, right? And then what we'd like to do is match those each of those terms to the monomial in the quadratic representation. So if we take our example here, 1x, xy, right? 1x, xy, and we have these M11, M22, M33, and so forth, right? 21, M31, and so forth, M32, right? Each of these corresponds to a monomial, right? When you multiply out the quadratic representation, each of them has a corresponding monomial. So M11 has 1, and M33 plus dot 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 plus M33 has x squared y squared. And of course there's the one with the ambiguity here. Actually, I think maybe this one doesn't have ambiguity. I have to search for the ambiguity there. But in any case, each of those elements has a associated monomial, right? And so what we're going to do is take each of those elements, right? We create the vector form M11, M21, M31, M12, M22, and so forth, M32, yada, 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 right? And then multiply them by this AZ here, which the A does nothing more than pick out the monomial in Z, which corresponds to that M. right? So for example, if this was 1, so here we're looking at 2 degree, we have to double our degree. So our monomials look like 1, x, x squared, x, y, y squared, and there's there's a y in there as well, right? So M11, for example, corresponds to the monomial 1. So the A matrix here just has a 1 here, and all the rest are zeros. M21, right, corresponds to the monomial x. So it has maps x over to that element, and then we have zeros. And let's see, M31 corresponds to xy. So we look for xy here. It's the 4th element, 0, 0, 0, 1, and then some more zeros, and so on. So it's just the element of the ZD which corresponds to that coefficient, right, when we write out the quadratic representation. Now, we can automate this system because there's a closed loop form solution to this. So if we just look at that quadratic representation, we can write it out in this. This is the expanded quadratic representation, right, where we've taken the square of each of those monomial terms, right? So Mij, that coefficient, has monomial alpha I plus alpha j. And then we just look for the corresponding monomial in Z2D. So we're looking for we take the sum of those 2 monomial coefficients, right, because we multiply them to the exponents add. So we add the corresponding coefficient here for M11 or Mi. So this is the monomial for MII or Mi in the vector form of M. For Mi, or it's the monomial for the, if we form the vector matrix of M, it's the ith element of that. Right. And so here we've just got P is the dimension of ZD here, right? So the formula is we take the index of that M, and then we mod it with P. So we subtract the highest. This just tells you which row and column you're in. So this gives you the row, and then this gives you the column corresponding to the larger M. So this maps the elements of vector M to the matrix M, right? So maps these two things. Okay. And then if that's equal to the monomial in ZD, then A just, that's the 1, right, from over there. And everything else is 0, right? So there's only one non-zero element in each row here of A. Right? So that allows us to then to put the quadratic representation using the matrix M in a vector linear representation of the new decision variable or the modified decision variable here. Right? And so if we want, for example, now this to equal to the Lyapunov function, C transpose ZD, in this case 2D of x, right? We just need to constrain vec M transpose A equal to CT, right? Our other decision variable. And that constraint, well, this is not a decision variable, so I shouldn't blew it, but I blew it. So those are decision variables, and now we've eliminated the x, the independent variable, from the formulation, right? Because equality of these two forms, right, is just equivalence of the coefficients of those monomials. So a polynomial is equivalent to another polynomial if and only if all of its coefficients of all its monomials are equal in the linear representation. So we have a linear constraint now on the decision variables, which, with the positivity of M, enforce the constraint that via the Lyapunov function to be sum of squares. And of course, we can also apply this to the derivative as well. So summarizing here, right, for Lyapunov stability, we're looking for this Lyapunov function here, z transpose qz. We represent it in the linear representation here, right? So sorry, actually, this is there's a dot there, right? So this positivity constraint is all well and good. We don't actually need to do anything with it because it's a decision variable by itself. And now we want to constrain its derivative, right? Which is this is the derivative is equal to z of x, 2 times the z of x, q. So the nabla form of this. Actually, I'm going to just do this in the linear representation because it's taking the derivative is easier in the linear representation, or taking the gradient of it, because we want to take gradient of v. That's what we're doing right now. So let's represent this this quadratic form in linear representation, right? So equals nabla, and now the linear representation of this quadratic representation is just the vector form of q transposed a. So v of x is z d of x. And of course, now we take the gradient of that. That's a wrong gradient. It's Laplacian. And then we get gradient of v of x. And we apply a gradient to this side, but it's a gradient with respect to x, but x doesn't appear in any of these terms, so we can move it all the way over here. Equals vec q transpose a vec z d of x, right? And now we want that equal to a sum of squares, right? But it's a little bit tricky now. And here I'll just add the other sum of squares coefficient on the other side. Here maybe a new decision variable d transpose a z 2d of x. That's also a decision variable. Of course, we have a bit of a problem now because we have the gradient of 2d, but of course, if we look at the gradient of that vector of monomials, we can also represent it, right? So if this is the gradient of 1x, let's say x squared, for example, then what is that gradient? It's 0, 1, 2x, for example. And then we can write the linear representation of that in terms of the original x vector of monomials, x squared. So this is equal to let's see, here we have all 0, 0, 0, 0. And here we've got 1, 0, 0, right? Because 1 is equal to 1 times that. And next we've got 2 times x, so 0, 2, 0. And then we can continue on down. So each of those monomials in the gradient, or each of those terms in the gradients, has a coefficient times this monomials. And so we can label this a matrix B, which we can formulate a priori because we know what this ZD is. And so we can just write this as equal to vec of Q transpose A. And now we write this as B Z 2D of X equal to D transpose. That's the decision variable for our SOS variable. And we have a negative sign here, of course. Actually, we need a negative sign. And we actually have to multiply by f of x, but we're not going to talk about that. So a z2d of x. So this gives us a constraint of this term equal to this term. So here, that's what we're doing here, right? There's our derivative, and here's our SOS variable. Right, where that was our D that we used right over there. Right. Decision variable, decision variable, decision variable. So again, an equality constraint on from this equal to this. So that's in principle how one does this, right? It's just a matter of moving from the quadratic to the linear representation, representing the monomials using these matrices on the coefficients. In practice, of course, you'll almost you wouldn't set this up by hand, right? This is a process which has been automated through numerous software tools. And so now I'll just go through some of those software tools which do this. And that's just what I pointed out in the previous two slides is what's going on internally in these software packages. Right? So you're probably most familiar with Yalmip at this point. So hold on a second then. So it's worth noting that Yalmip does have an SOS package. I'm not a big fan of it because it's kind of clunky, but it does most of what we want some of the time. But it's not as flexible as you would like. But in any case, I'll go over that first. So again, right, you can go to the SOS, the Yalmip manual here, and it'll tell you how to manipulate sum of squares polynomials. I'll give you some hints from the manual, right? So first of all, what I don't like about it is its treatment of independent variables. So basically, if you're doing a polynomial optimization problem or optimization of polynomial problem, you have to declare the independent variables using the command sdpvar. Which is extremely confusing, I think, because sdpvar usually denotes decision variables. And here it's now denoting independent variables. So I'm unhappy with that treatment. I think that's like almost disqualifying right off the bat. But in any case, that's how they do it. So if you're familiar, if you like using Yalmip, it has some functionality, but not. It's limited, and I don't like how it's presented. So in any case, in this case, we're looking for a proof that this polynomial, which is the same one we had before, is positive. Right? So basically, we add a constraint. So we define our polynomial in those independent variables, IVs, right? So not decision variables. There's no decision variables here yet. In fact, in this problem, there are no decision variables at all. There's only a constraint. The decision variables are declared internally, and you never see them. So you define your P in terms of the sdpvars, and then you add a constraint. So you declare your constraint structure, and then the constraint looks like this, SOSP, which basically constrains P in the cone of SOS polynomials. So that's what this does right here. So if there were decision variables in here, you could use this. Unfortunately, there's no way of actually declaring decision variables on the coefficients. There's no way of explicating exactly what the decision variables are, which is one of the big reasons I don't like Yalmip on this case. Yalmip is great, just not for SOS in my opinion. Anyway, so this declares a SOS variable on P, which again has no decision variables in it. And then you use a slightly modified version of solve to solve SOS on that set of constraints. You can also add an objective function, but we have none in this case. Yeah. Again, if you want the SOS certificate, the squared representation, you can run this code and you can use SOS display to spit out your certificate. And it shows you this, right? Your squared. Well, this is actually doesn't look like a squared representation to me, but that's what it spits out. So it's just displaying the corresponding polynomial representation. Great. Again, right, Yalmip, not my favorite tool for this problem. The best one by far, I think, is SOS Tools, which hasn't been getting as enough updates as of late as it should, but it's still, I think, the most reliable tool for solving these SOS problems, converting them to LMIs. And so you can go to the SOS Tools website here. There has a number of mirrors, so if that one doesn't work when you get this, then try another one. Just search for SOS Tools, I'm sure you'll find it. In this case, it declares the independent variables in a better structure using the PVAR structure. So this is for declaring independent variables. And I like that because it separates from the decision variables. Right. Which we'll talk about decision variables a little bit more later. So you declare your independent variables, then you can do anything you want with them because it puts those independent variables in a structure. So you create a polynomial here, P. The next step is to initialize an SOS program. So you initialize it by telling it what the independent variables are, independent variables. So you give it a little table of independent variables, declare an SOS program, and it spits out a program structure, which is also nice because you could then play around with the program structure and look at it. It's not all internal. The downside is that you have to pass this program structure back and forth when you're adding inequality constraints and objectives and so forth. So this is the program structure, and you have to you have to make sure you use the same program structure, or you're going to branch out your program. So it has to go into every subsequent command. So the next one is adding a constraint that P be sum of squares. And it does that by this command SOS init. So basically, there's more functionality I'll go through in a minute. But basically, you give it the program structure. You have to pass it back in. It then adds the constraint that P be sum of squares to the program structure and passes it back to you. Right? So it passes the program structure back. You then use that modified program structure, and here we're just going straight to the solver. You pass the modified program structure back into SOS solve, and it returns a third program structure which has the solution, right? Now has the solution. And it also has tools for displaying the SOS solution as well, but I don't have them on this slide. What's also nice about the SOS tools is that it has an extension to matrix-valued polynomials, which is important because when we talk about robust control, right, we're talking about matrix-valued polynomials. So a matrix-valued polynomial is just a matrix, each of whose elements are polynomials, right? M11 of x comma y and so forth. Right. So in this case, really the idea is the same. The only difference is that we're now creating this quadratic representation. The ZD, the vector of monomials, is the vector of vector-valued monomials, right? So this is a monomial Z, 0, another monomial y, z, I'm sorry about that, y, z, 0, another monomial 1, obviously this isn't a complete list, another monomial, oh sorry, that's on the wrong spot, 0, 1, another monomial 0, y. Obviously, once you get to vector value, the number of terms in your monomials doubles because, right, basically we're just going zd, 0, and then 0 ZD. So twice as many monomials in this structure. So the size of your SOS program doubles, right? But in any case, you construct such a thing, right? And then you search for a positive matrix, which is equal to, again, using the linear and quadratic representation. Again, using ZD of x here, C transpose. But now this is not actually a vector, but a matrix. And this is also matrix valued. It has, right, that form. So if you can find such a positive matrix, right, you can take its square root and construct a certificate that the matrix is positive as well, right? Q transpose, right? And then you just multiply it on the left and the right, right? So this is Q Z D of X, where this is vector valued, so we can make it 2 or something like that. And then a 2 by n matrix, or 2 by k matrix times a k by 2 matrix, right, gives you a 2 by 2 matrix, where each element, right, is a bunch of is a vector times a set of monomials, right? A vector times a set of monomials, and so forth. So you get, in this case, four polynomials in your matrix, right? And so it's the same on the left and the right. This is QZD, and this is QZD transpose. Right, and so you get a matrix squared, right? A Q, let's call it Q of X, transpose Q of X, and I should add Y there as well. And of course, any square matrix at any given value of X and Y is positive, semi-definite, and so this shows that this is positive semi-definite matrix for any X and any Y. So, and we just double up that notation with matrix valued sum of squares, so we can make a 2 by 2 if we like. But I think the notation is relatively clear. So for example, now if we want to show that this matrix is positive semi-definite, right? Using the same example on the previous slide. Again, independent variables X and Y. Now we just declare a matrix, right, in standard matrix notation. M11, M12, M21, and M22. Where does M22 start? There. Sorry, that's that one. Right. So you just declare that matrix of polynomials, and then you declare a program in your independent variables Y and Z. And then the matrix inequality constraint is almost identical to the scalar one, right? We just throw the program structure back in and add the constraint through which is somewhat cumbersome title. I don't really like it. SOS matrix unique, which makes M a sum of squares, adds that constraint to the program structure. You spit it back, solve it, gives you a solved program structure. And then we can reconstruct that matrix on the previous slide, although it's not that simple. Of course, those are the simplest possible cases. That was where our decision variable is really non-existent, right? In the real case, of course, we're looking for a Lyapunov function where we have a set of decision variables, right? So the polynomial is itself a decision variable, which is parameterized by this vector c. Right? So v is the decision variable. In this case, of course, right here we've got this is our vector field, f of x comma y. Right? Is that vector there? And we're looking for a stability proof, right? So we're going to use SOS tools because it's better. We have decision variables x and y. We just declare that vector field, say what it is. It's just a vector, right? Here's first polynomial, here's the second one. Initialize an SOS program, 2 independent variables here. Now, here we have the question, here we have an additional step where we need to declare a decision variable, right? So the command for declaring a decision variable, essentially declaring the C, but you don't see the C. It's like under the hood. But there's a tool for declaring an SOS decision variable, and actually there's a separate tool for declaring an indefinite decision variable. So this one declares a decision variable of this form with the constraint that it's sum of squares, right? So decision variable as a decision variable and SOS constraint. So SOS it's in SOS tools, SOS because it's adding that SOS constraint, and var because it's a decision variable. Of course, you have to tell it what the degree of the polynomial you want to parameterize is. So you can't make it indefinitely large. So you have to tell it what this vector of monomials here. And so actually it has a separate tool for declaring a given set of monomials. So that syntax is you give it independent variables and the degrees you want, from degree 0 up to degree 2 in this case. And now you plug that vector of monomials in here, and actually it's not this D, it's actually the quadratic D in this case, so I shouldn't actually say that. Right. So this declares the internal variable Q and the variable that you see, which is V, right, the decision variable. So it's a decision variable, decision variable, decision variable. To highlight that other places. Now, so anyway, so as I was saying, right, you declare the vector of monomials in the quadratic representation. So that means that actually, in this case, our variable v will have degree 4 or less, right? Because it squares this vector of monomials. So has degree 4. Right. So again, right, because the SOS var uses a quadratic representation. Then to make it strictly positive, otherwise it would return 0, we add a very small quartic term here, 001 times x to the 4th plus y to the 4th. Then what we do is we set v of 0 equal to 0, because otherwise it would not necessarily be so. So don't forget this. I know we haven't focused on it so far, but it's an important constraint, otherwise it'll do weird things. To do that equality constraint, v of 0 equals 0, we use this command eq, which sets whatever's on the right in the second argument equal to 0. Right? And so what do we want to be 0? We want v, using the substitution command, v where we substitute the independent variables x and y with 0 and 0. So x goes to 0 and y goes to 0. So that substitutes in those particular values, add as a single constraint, v of 0 equals 0. So basically zd of 0 q zd of 0 equals 0. All right, so that's does a substitution and then sets the equality constraint. Again, we have to get the program structure back. There's also a command for constructing the linear representation of the derivative. So we have this command nabla-v, where we just differentiate the first and the with respect to x and with respect to y. So we construct partial x v, partial y v, right? And that's nabla-v. Right. So we construct that nabla-v, and then we construct the derivative v dot equals nabla-v transposed with f, right? And so there's that nabla-v transposed with our vector field, and we have a negative sign in front of it. And we use ss and eq to constrain this thing, here the negative sign, to be sum of squares. So that's what this unique does right here. And then, so we've constrained v to be greater than 0, we've constrained v dot to be less than 0. And so we're now ready to solve our program, so we send it back to SOS solve. It returns the solved program structure, and then we can actually get the solution for what that Lyapunov function is using SOS get sol. So the inputs to that are the variable that we want, and then the actual values of this this eternal decision variables, which are encoded in this now solved program structure. You can't use this command, of course, until you've run this command, right? So this solve command has to come before the get solve command. Otherwise, there's nothing to get. We can do this with Yalmip, although it's, again, a little bit more annoying. But for nonlinear stability, it's certainly doable. So again, we declare our independent variables, constructor vector field again. Now, for our decision variable, we have this command polynomial. So that gives us our decision variable. And now, the inputs to that are the independent variables in v of x. And now, this is the degree in the linear representation. So this is the actual degree of our decision variable, which gets popped out, which is v. It also conveniently pops out the coefficients, variables of that decision variable, so that actually we can enforce v of 0 equal to 0, assuming we know what the monomials are, and that's actually not obvious, but the first element of that coefficient corresponds to the monomial 1, right? And so basically to constrain v of 0 to 0, we just have the no scalar term, right? No term which doesn't have an x or a y in it, right? So this declares a polynomial decision variable. This is adding a constraint that v of 0 equals 0. And now we can add a constraint that v is strictly positive, right? By v minus 0.001 x squared plus y squared. Make that greater than or equal to 0. So then it just makes v greater than or equal to 0.001 x squared plus y squared, right? And we again use that SOS constraint to make this equal to SOS, or in sum of squares. There is a command in Yalmip. The Yalmip's fairly limited in its polynomial manipulation capability, but there is a command for constructing the Jacobian. So this actually just creates a gradient of v. So there's a built-in command for doing that. It's relatively useful. And then, of course, we construct v dot. So this is negative v dot. And we constrain negative v dot to be greater than or equal to 0 by making it a sum of squares constraint, using that SOS constraint. And then we solve it. Here's our constraint form, and it wants us to give us this VC as well, just for good measure, because that's a decision variable, because we added that constraint to it. Decision variable, decision variable, decision variable. And as with SOS tools, right, this allows us to prove stability, global stability in this case, of this Moore-Greitzer model from a jet engine. I think this is actually a ODE version of Berger's equation. I think this comes from Berger's equation, which makes me think I'm hungry. Right. So those are the two main ones I want to talk about. There's another one, SOS opt, which is rather more recent. I'm not sure it's much better than Yalmip, however, but maybe it's improving with time. Created by Pete Seiler in Minnesota, although he recently moved to Michigan. But I think the site is still at Minnesota. He hasn't moved the site to Michigan yet, as far as I know. And of course, I can plug my own version of SOS tools, which has some more capabilities, so the ability to create matrix variables per se, positive matrix variables by themselves. However, for this class, you don't need this. In fact, actually, for this class, I actually have a custom set of sort of simplified SOS tools, which I'll distribute through the website. So to conclude this lecture, more or less, right, here's that Moore-Greitzer model. This is the Lyapunov function that comes from SOS tools. And here, if you've seen, remember this picture, I've shown it a couple times. This is actually the vector field and the level sets of that Lyapunov function. So, gamma. So remember, you can use SOS getsol to get the Lyapunov function. And then you can plot the level sets by just plugging in the points less than or equal to gamma. So create a heat map and plot those level sets. So we conclude with a couple notes. We've shown how to solve optimization of polynomial problems, where we've made a couple restrictions. First restriction is bounding the degree of the polynomial. B of x equals c transpose z d of x. And the second constraint is replacing v of x greater than or equal to 0 for all x with v of x equals to sum of squares. And we argued that there is a, this is not entirely inaccurate. It's very close to being necessary and sufficient, but it's actually not actually necessary because, as from Hilbert's 17th problem, sum of squares is not necessary and sufficient. It's sum of square ratios of sums of squares, right? So, technically, if we want necessity, we should be looking for a sum of squares over a sum of squares. Unfortunately, if this is a decision variable, right, and this is a decision variable, and this is a decision variable, this is not linear, right? We can move this decision variable over here if we want, but it's still bilinear in these two decision variables, so we can't actually search for it. But we can, of course, use Artin's representation, but that requires us to assume that our Lyapunov function is strictly positive, which is, of course, not true. However, in that case, we get around this bilinearity because this is a fixed polynomial here. So if this is a decision variable and this is a decision variable. So basically what we're saying here is that we can, if necessary, and it's very rarely necessary, we can reduce the conservatism of the SOS condition. Conservatism, can't spell conservatism. By adding this term, the sum over xi squareds, right? Now, in general, you should not do that because it increases the degree, increases the complexity, and so on and so forth. But remember, of course, polynomial positivity is an NP-hard problem, so you would not expect a finite time or a polynomial time way to test it, which is the SOS, right? SOS gives you a polynomial time test for SOSness, but it does not give you a polynomial time for positivity because of this little issue here with the sum over xi squareds, or this issue here with the ratios of sums of squares. But that's okay because, right, our goal here is not to solve NP-hard problems exactly, but to relax them or construct sequences of optimization problems which converge to necessity as we increase the complexity. And our metrics for increasing the complexity here is adding these sum over xi squareds, increases complexity. Now, for all practical purposes, if you're looking for Lyapunov functions here, using the SOS Lyapunov functions is necessary and sufficient for stability in most cases. And in fact, we have proofs that there exists sum of squares Lyapunov functions for polynomial vector fields. In fact, we haven't authored that paper if you want to go to my website. In general, positivity of polynomials in general, however, it's not necessary and sufficient. There's a very well-known and famous example of polynomials which are not sums of squares but yet are polynomial or positive. So this class are the class of Motzkin polynomials. So here's a particular Motzkin polynomial. It looks like this. You can see it's positive. It gets very close to non-negativity here, right? That's p of x equals 0, right? So it's very close to being so the positivity, the semi-definite part is tight. It gets down to 0. And it's not in sum of squares. There is no sum of squares representation. However, right, We can apply the Artin construction by adding xi squareds to the power d. And the first one we get is just to the d equals 1. We get x squared plus y squared plus 1. And if you multiply that sum of xi squareds times the Motzkin polynomial, that is sum of squares. Right? So our condition doesn't work on the first iteration, but it does work on the second iteration. So our sequence, we only need to go to d equals 2 in order to get a necessary and sufficient condition for this polynomial by itself. Right, so that's a fairly deep dive into sums of squares of polynomials and how they can be that class of optimization problem can be represented using LMIs and solved using LMIs. And we've covered a couple tools that allow us to do that. In the next lecture, we'll address the question of global versus local positivity, because all of the results in this one have been global. But clearly for nonlinear systems, global stability is rare. So in the next lecture, we'll talk about how to enforce p of x greater than or equal to 0 for all x in some set, x, say, such that gi of x is greater than or equal to 0. But that will have to wait until the next lecture. So I'll see you then.